Let's talk about light. Not the kind that just lets you see things, but what light really is, and how it interacts with the universe at the smallest possible scale. Quantum Electrodynamics, or QED, is the theory that explains how light and matter talk to each other. At first, that sounds simple, but it turns out to be one of the strangest and most accurate theories ever created. In QED, light is not a smooth wave filling space. Light comes in tiny packets called photons. A photon has no mass. It cannot slow down. It always travels at the same speed. And photons are the messengers of the universe. Whenever two charged particles interact like electrons pushing or pulling each other, they do it by exchanging photons. You can think of it like this. Particles don't touch. They communicate. Now here's where things get weird. When a photon travels from one place to another, it does not choose a single path. Instead, according to QED, the photon explores every possible path. Straight paths, curved paths, ridiculous looping paths, paths that seem completely pointless. All of them. Of course, we never see all those paths. What we see is the final result. The reason is interference. Each possible path contributes a tiny signal. Most of those signals cancel each other out. Only a few paths reinforce each other. And the paths that survive are the ones that look like the classical path, the one we expect. So light appears to travel in a straight line. But underneath, it's doing something far more imaginative. This idea is not philosophy, it's math. And it works with astonishing precision. QED predicts experimental results to more decimal places than any other theory in science. But here's the most important lesson. QED tells us that the universe does not behave the way common sense expects. It does not choose the simplest path. It does not follow human intuition. Instead, nature tries everything and lets the mathematics decide what survives. That's the uncomfortable beauty of quantum physics. We can calculate it, we can test it, we can use it to build technology. But deep down, we don't get a comforting picture of why it works this way. And that's okay, because physics is not about making reality easy to accept. It's about discovering how reality actually behaves even when it refuses to make sense. And light, through QED, gives us one of the clearest windows into that mystery. People often learn that light is a wave, and that's not wrong. It explains reflection, refraction, interference, all the familiar things. But it's not the whole story. When we look closer, much closer, light stops behaving like a smooth wave and starts behaving like something else entirely. In quantum electrodynamics, light comes in little chunks. We call them photons. A photon is not a tiny billiard ball. It has no size you can point to. It has no mass, and it cannot sit still. If a photon exists, it moves always at the same speed. So what does a photon do? A photon is a messenger. It carries energy and momentum, but more importantly, it carries information. Whenever charged particles interact electrons, for example, they don't reach out and grab each other directly. Instead, they exchange photons. You can imagine two electrons having a conversation. One electron throws a photon. The other one catches it. Then it throws one back. That exchange is what we experience as electric force. So when electrons repel each other, it's not because of some invisible push. It's because they are constantly trading photons. Light, in this sense, is the language of the universe. It's how particles communicate. Now, here's the strange part. These photons are not always the light you can see. Most of the photons exchanged between particles are virtual photons. They can't be detected directly. They don't behave like ordinary light. But mathematically, they are essential. Without them, atoms wouldn't exist, chemistry wouldn't work, your body wouldn't hold together. So light is not just illumination. It's structure. It's interaction. It's the reason matter behaves the way it does. And this is where QED becomes remarkable. Instead of trying to picture photons as tiny objects flying neatly through space, QED tells us something more honest. Don't imagine too much. Just calculate what happens when particles exchange photons and the answers come out right. Extraordinarily right. More accurate than any other theory we've ever built. That's the uncomfortable lesson. Nature does not care whether we find the picture intuitive. It only cares that the rules work. And in QED, light is not a wave. not a particle in the everyday sense. It is a quantum messenger carrying the conversations that hold the universe together. Once you see light this way, you stop asking, what is light really? And you start asking a better question, how does the universe manage to work at all? How light finds its way, the all paths idea. Let's imagine something very simple. You shine a beam of light from a flashlight to a wall. Common sense says the light travels in a straight line, hits the wall, and that's it. And at our scale, that picture works perfectly well. But when we look at light on a very small scale, the quantum scale, that picture turns out to be incomplete. According to quantum electrodynamics, a photon does not choose a single path from start to finish. Instead, something much stranger happens. The photon explores every possible path, not just the straight one. It considers paths that curve, paths that zigzag, paths that loop around, paths that look completely ridiculous, all of them. Now, this does not mean the photon is consciously trying things out. It's not deciding anything. This is simply how nature behaves when we describe it accurately with mathematics. Each possible path contributes a tiny effect, like a little arrow with a direction and a size. Some arrows point one way, some point the opposite way. When you add them all together, most of these contributions cancel out. They destroy each other. Only a small family of paths survives the ones near the path of least time, which looks like a straight line. That's why light appears to travel straight, not because it only takes one path, but because all the other paths cancel themselves away. So the straight line is not chosen. It's what remains. This idea sounds outrageous, but it explains interference, diffraction, reflection, all the strange behaviors of light with incredible accuracy. And here is the beautiful part. This rule doesn't apply only to light. Electrons do the same thing. Atoms do the same thing. Everything in the universe, at a deep enough level, explores all possibilities, and reality is the sum of what survives. Nature doesn't say, which path makes sense. It says, let everything happen and see what cancels out. That's a completely different way of thinking from everyday logic, but it works extraordinarily well. And that's the lesson. Quantum physics doesn't give us a comfortable picture of reality. It gives us a correct one. Light doesn't know where it's going. It doesn't need to. The universe simply allows every possibility, and mathematics quietly removes the ones that don't matter. What we observe is not the path light chooses. It's the result of all the paths light was allowed to take. Why, we don't see photons wandering everywhere. When you first hear that a photon takes every possible path, the natural reaction is disbelief. If light really explores all paths, then why don't we see it wandering all over the place? Why does it look so well behaved? Why does it seem to travel in a straight line? The answer is not that those other paths don't exist. They do. The answer is that they cancel each other out. To understand this, we need to change how we think about motion. In quantum physics, we don't say, this is the path the photon takes. Instead, we say, each possible path contributes something. You can think of each path as contributing a tiny arrow. That arrow has a length and a direction. Some arrows point one way, some point another way. Now imagine adding up millions and millions of these arrows. Most of them point in random directions. When you add them together, they cancel out. They destroy each other. Their total effect becomes essentially zero. Those paths still exist mathematically, but they leave no visible trace in the final result. Only a very special set of paths behaves differently. These are the paths close to the one that takes the least time. Along those paths, the arrows line up. Instead of canceling, they reinforce each other. They add together. And when they add together, their effect survives. That surviving contribution is what we observe as the photon's motion. So the photon doesn't choose the straight path. The straight path is simply the one that remains after all the other possibilities erase themselves. This is why light looks classical at large scales. Not because quantum behavior disappears, but because quantum effects cancel out so efficiently that only the classical result is left behind. And this is a profound lesson. Nature does not eliminate possibilities by forbidding them. It allows everything, and then lets interference decide what matters. Reality is not built from certainty. It's built from an enormous number of possibilities, most of which quietly cancel each other out. What we see is not the full story. It's the small remainder, the part that survives after the universe finishes adding everything up. And that's why light looks simple, even though underneath it is doing something astonishingly complex. One of the hardest things about quantum physics is that you can't see what's going on. The equations work beautifully, but they're abstract. They live on paper, not in your imagination. So the question is, how do you think about particles interacting when the math is too complicated to picture? That's where Feynman diagrams come in. A Feynman diagram is not a photograph of reality. It's not a literal picture of what particles are really doing. It's something much more useful. It's a visual bookkeeping tool. Instead of writing long equations, we draw simple lines. A straight line represents a particle, like an electron. A wavy line represents a photon, the particle of light. And when lines meet at a point, that means an interaction. That's it. Now here's the important idea. When two electrons repel each other, they don't touch. They exchange a photon. In a Feynman diagram, that interaction becomes obvious. You see one electron coming in, one going out, and a photon exchanged between them. What took pages of mathematics suddenly fits into a simple drawing. But don't be fooled. The diagram doesn't say how the interaction happens in time. It doesn't tell you what path the photon takes. It doesn't describe a tiny movie playing inside space. What it does is tell you how to calculate probabilities. Each diagram represents one possible way an interaction could occur. To find the real answer, you add up the contributions from all possible diagrams. Some contribute a lot, some contribute very little. Together, they give the final result. The genius of Feynman diagrams is that they turn invisible quantum processes into something we can reason about. They let us see relationships instead of drowning in equations. They don't simplify nature. They simplify our thinking. And that's why they change physics. Not because they made the universe easier, but because they made it possible for humans to understand it at all. What QED tells us about the universe. One of the strangest lessons of quantum electrodynamics is this. The universe does not run on certainty. In everyday life, we expect things to be definite. If you throw a ball, it follows one path. If you flip a switch, the light either turns on or it doesn't. But at the quantum level, nature doesn't work that way. In QED, we don't ask, what will happen? We ask, what is the probability that this will happen? When particles interact, there is never just one outcome. There are many possible outcomes, each with its own likelihood. Nature doesn't choose a single path in advance. It allows many possibilities to exist at the same time. And here's the key idea. These possibilities don't compete by logic or intention. They compete by interference. Some possibilities strengthen each other. Some cancel each other out. What survives is what we observe. So nature doesn't ask which path is correct. It asks which paths remain after everything is added together. That's a completely different way of thinking. It means the universe is not built like a machine with gears clicking into place. It's built like a vast calculation, constantly summing possibilities. This doesn't mean the universe is random in a careless way. The probabilities are precise. They can be calculated to extraordinary accuracy. QED gives predictions that match experiments to more decimal places than any other theory we have. So the universe is not uncertain because it is sloppy. It is uncertain because certainty is not how reality works at its deepest level. What we call reality is the statistical outcome of countless microscopic possibilities. And that's the uncomfortable but beautiful conclusion. Nature doesn't promise exact answers, it promises accurate probabilities. And somehow, from that uncertainty, everything we see emerges. Let me tell you something strange about light. We like to imagine light as a neat little thing, a wave, or a particle moving politely from one place to another. But nature is not polite. Nature is weird. In quantum electrodynamics, QED light is not a smooth wave, and it's not a tiny bullet either. It's an event, a probability, a conversation between charged particles. When an electron moves, it doesn't send out a clear signal saying, "Here I am." Instead, it explores every possible way it could interact with light all at once. Straight paths, crooked paths, ridiculous paths that go backward in time. And here is the miracle. When you add all those possibilities together mathematically, the nonsense cancels out, and what remains is the simple, predictable world we observe. That's why QED works so well. It predicts the behavior of light with astonishing accuracy, better than any theory humans have ever invented. But don't be fooled. Just because the equations work doesn't mean we understand what's happening. We don't know why nature chooses this bizarre method. We only know that it does. And that's the lesson quantum physics teaches us, a humbling one. Reality is not required to make sense to us. It only has to be consistent with experiment. So when you look at a beam of light, remember, you're not seeing a thing. You're witnessing the sum of countless invisible possibilities, agreeing just enough to become reality. And if that feels uncomfortable, good. That's how you know you're starting to understand.